welcome to this Learning Machine Seminars, everybody. And especially welcome to Stéphane Dascoli, who is a Ph.D. student at ENS Paris and Facebook AI research in Paris. But perhaps you're now Meta AI.
I changed my logo like literally 5 seconds before this.
Yeah. So Stéphane works on understanding deep neural networks and their generalization properties of course, in overparametrization regimes, such as sort of the normal modern regime. And today you're going to give a talk on the topic of double descent. And so I now hand over to you, Stéphane. The floor is yours.
Yeah, thanks a lot, Olaf. So it's a pleasure to be speaking for you. So I'm going to be speaking broadly about double descent. So as I don't know exactly the background of everyone, just feel free to interrupt me, ask questions, ask me to slow down, to go faster. Yeah, let's make it really interactive. And yeah, so basically I'm going to give this talk in 3 main parts. I'm going to start with a quick crash course on double descent, what it means, and then I'm going to try and reconcile it with the classical wisdom of bias-variance trade-off. Then in a third part, I'm going to try and show that this modern double descent we've been studying over the past 5 years actually is different from the one that was known much earlier in the 90s. And then in the last part, I'll discuss the role of data structure, which has been ignored in most of the theoretical work on double descent. So yeah, let's start with a couple reminders on double descent. So if we start from the basics, so classical learning theory tells us that the more data you have, the better your model is going to generalize. And this, of course, makes total sense. What is a bit more intricate is what happens if you have a learning model and you make it bigger, if you give it more freedom, more parameters to learn with. And what learning theory tells us is that in this case, we expect to see a U-shaped curve for the generalization performance, in this case, the generalization error. Indeed, the price to pay for achieving low bias is typically to have a high variance. So if you have a small number of parameters in your model, typically you're going to underfit your data set. If you have too many parameters, you're going to interpolate your data, but typically your variance is going to be large, and that's going to give you poor predictive power. And so ideally, you want kind of a sweet spot in between these 2 extremes to extract just the right information from your problem. And this surprisingly turns out not to be true in deep learning. So I'll kind of give a spoiler and then try and explain, give some intuition on this. So in deep learning, what we observe as we increase either the number of parameters, which I'm going to call P from now on, or the number of training examples that I'm going to call N, is this kind of double descent curve. Now let's start with the one on the right here, which is what we call sample-wise double descent, which is what happens as you increase the size of your data set. Well, this actually kind of sticks not too badly with our classical picture, which is that generally speaking, the test loss does go down as we increase the number of training examples, as we could expect. However, you do see that there is this odd peak, which we see when the number of training examples is equal to the number of parameters, or at least of same order of magnitude. And so we're going to try and understand what this is due to. And the second type of double descent, which we're going to call parameter-wise double descent, so which occurs when you increase the number of parameters. So it looks the same, but here it's much more surprising because remember that the classical learning theory tells us that we expect a U-shaped curve, so which increases to the right of the curve. And here, again, we see this peak, but even more surprisingly, we see a decrease of the test loss as P goes to infinity. So first of all, I'm going to give you some very basic intuition on why we can observe this kind of curve, starting from the most basic kind of learning model we could imagine, which is polynomial regression. So here, we're going to take n equals to 5 data samples, and then P is going to be the degree of the polynomial we're fitting, so the number of coefficients we have to learn. And so if we take P equals to 0, of course, you only have a constant to learn with, so your test error is going to be high. If we take P equals to 1, we have a linear function, so it's going to increase a bit. So we're going to get better performance, but there's going to be a point at which you're going to get poor performance, which is exactly when p is equal to n, when the degree of your polynomial is equal to the number of data points. Well, you know that there's a single solution, which is the interpolating polynomial, and typically this polynomial is going to have high variance. It's going to look like this squiggly curve we have here. And so the test error is actually going to be kind of bad, just like when you had a very small degree polynomial. And then one can wonder what would happen beyond. So if we still increase p, well, we know that when p is larger than n, we actually have multiple solutions to the problem. We have multiple interpolating polynomials. And so the test error is going to depend on which polynomial we choose. So if we don't regularize, we're going to have a very high variance polynomial, and test error is going to become worse and worse, just as we expect from the U-shaped curve of classical learning theory. But if we do apply regularization, then we're going to see the test error decreasing, as we can see with the green curve here, which is doing, of course, much better than the orange curve. So you can see that even in this very basic model, you can see these two kinds of behavior past the interpolation threshold, and you can see why we can have this peak when p is equal to n. But what is interesting here is that in deep neural networks, typically we observe this decrease of the loss when p goes to infinity, even in absence of explicit regularization. And so that's what we call implicit regularization in deep learning, and this is something we're going to try and understand in this talk. A second very basic example to introduce double descent would be linear regression. So you've probably all seen this formula for linear regression when you try to overfit with a linear model some labels y. Well, you know that the optimal formula for your weights w is going to be given by this formula here, where we have essentially the covariance of the input data, where you take the Moore-Penrose inverse, and then you have the input data again, and then the labels. And what's interesting here is that this data matrix X is of size p times n. So remember, in linear regression, the number of fitting parameters is just the input dimension. And actually, it turns out that this covariance matrix XX transpose is going to have very small eigenvalues when p is equal to n, because essentially X is going to become full rank. And it's going to have very small eigenvalues because it's going to be pretending to be higher rank than it really is. And what this means is that if XX transpose has very small eigenvalues, then its inverse is going to have very large eigenvalues. And therefore, this matrix W star is going to have some very large components, and it's going to have a high norm. And this means that it's going to have high variance. This can be seen from simply the distribution of eigenvalues of XX transpose, which is known to be Marchenko-Pastour in random matrix theory. And you see that when p over n is equal to 1, you have these very small eigenvalues here. Okay, so we see that we can get some intuition on double descent from very simple examples. But now let's move on to maybe a bit more advanced model. So first of all, I'll just show you what this phenomenology becomes in the context of deep learning. So this figure is extracted from a paper in 2019, which was one of the first to observe the same phenomenon of double descent, but in deep neural networks. So this is a fully connected network, of which we're increasing the width of each layer. And we see the curve in blue exhibits this double descent curve, where we recognize a U-shaped curve in this underparameterized regime where we have a small number of parameters. And then exactly when the training error goes to 0, we get a peak in the loss, and then the test loss goes down as we overparameterize. Now, we also have two other curves on this figure. We have a green curve, and this green curve corresponds to what happens if we perform regularization, in this case, early stopping. And you see that, again, the test error goes down as we overparameterize, but we don't get the peak anymore. And the third curve we have is this orange curve, which is an ensembling curve, which means that what we're doing is that we're calculating the test error of an ensemble of 20 different models, which only differ by the initialization of the weights. And so we take a majority vote out of all these 20 examples, and this gives us a new model which has much lower test loss, okay? And what's interesting here is that, again, the peak at the interpolation threshold completely vanishes. But more than that, we see that past the interpolation threshold, the test error is essentially constant. And so we don't get at all anymore this reduction of test error as we overparameterize. And this already gives us a kind of intuition as to what is really happening as we overparameterize, is that essentially we must somehow be killing some variance due to the initialization, because when we ensemble, essentially what we're doing is just we're removing this variance due to initialization of the weights, because the only thing that distinguishes these 20 learners is their initialization. So this is what we're going to try and show here. What is happening to the bias and variances as we overparameterize? And I'm going to introduce once and for all this model that I'm going to be using throughout the rest of the talk, which is the random feature model. So originally this was introduced in 2008, not as a theoretical model, but actually as a practical model, which was a fast approximation for kernel methods. And the idea is that basically it's just a two-layer network, so one hidden layer, where the first layer of weights is fixed and we only learn the second layer of weights. And what's really good in terms of theory for this model is that what this induces is that the input dimension, which here we denote as D, so the number of pink nodes, is disentangled from the number of parameters, which is given simply by the number of weights in the second layer, so which here we're going to call P, which is not the number of blue nodes. This isn't the case, for example, if we think of linear regression, as we mentioned previously. In linear regression, your number of parameters is simply equal to the input dimension. And so you can't study overparameterization for a fixed task, because if you want to overparameterize, you also want to make the input dimension larger. So here we can really overparameterize independently of the learning problem. And this kind of model was recently shown to exhibit double descent by a paper by May and Montanari. What's going to be very interesting for our study is that this model also has a notion of initialization, because remember, as I said, the first layer of weights here is fixed to the initial value. And so this, in some sense, can be viewed as the random choice of the initial weights in neural networks. Because if you think of linear models, there's no notion of initialization. For linear models, all you do is you have this explicit formula for the weights. And so you don't even have to initialize, then run gradient descent. You can directly calculate the formula for the weights. Here, it's actually very similar. All we do to learn the second layer of weights is to use the exact same formula we did for linear regression, except that instead of having this original dataset X, we have a predicted dataset Z. Last reason for studying this model is that it happens to be relevant to the lazy regime of neural networks. So some of you may have heard of the neuron tangent kernel, which is a line of papers studying what happens when the weights of the neural network move very little. And essentially what happens when you move very little is that you're basically learning a linear model. Essentially, you're doing the order one Taylor expansion of your neural networks around the initialization. And in this case, what you're doing is doing a random feature model where the random feature vector is given by the gradient at initialization. So you're really lying in the tangent plane of the weights. Okay, so let's introduce a bit more annotations. So as I said, D is the input dimension, N is the number of training examples, and P is the number of parameters, so the number of nodes here. So our learning function is going to be given by this formula. And the ground truth, so the function we're learning from, is going to be simply a linear function plus some added noise epsilon. And so, of course, we're going to be interested in the signal to noise ratio, which is the norm of the teacher divided by the variance of the noise. So to train our model, as I was saying, we're going to simply use a mean squared loss with an added regularization term, which is controlled by this regularization constant lambda. And importantly, we're only learning the second layer of weights A. The test error is simply given by the mean square difference on a fresh example. Okay, and so what we're going to be interested in here is trying to see what causes the test error, which is going to be trying to decompose where how the various sources of variance affect our problem. So essentially what we're going to do is a sequential decomposition of the noise, because there are three types of randomness in our problem, which are the randomness in the noise applied to the labels of the teacher. There's the randomness of how you sample the first layer of weights of the random feature model, and there's the randomness of the input examples, which are all Gaussian, right? And so first of all, we're going to average our predictor over the noise in the teacher, and this is going to give us, of course, an average predictor which is closer to the ground truth than what we would have gotten by randomly sampling here. Now, once we've done that, we've removed the noise in the labels of the teacher. What we're going to do is remove the noise due to the initial conditions, so the initialization of the weights theta. And this, in some sense, can be viewed as what we do in neural networks when you do ensembling. We're averaging over the initialization. So we get an estimator which is yet closer to the ground truth. And finally, the last source of variance we need to remove is the sampling variance, so which is due to the randomness of the input data. So in our case, it's actually the randomness of the sampling of the input data, but for a neural network, you can think of this, for example, as the randomness due to the choice of the mini batch seeds, etc. Okay, now let's plot these various sources of error. So one important thing is that for our calculations, so they basically rely on random matrix theory and some tools from statistical physics, but we always have to go to the high dimensional limit when n, d, and p, so number of training examples, input dimension, number of parameters, all go to infinity, but at the same speed, so their ratios are fixed. Okay, and so let's look at what this test error curve, which is, as you recognize, a double descent curve, is stemmed by. So the first source of variance we decomposed is the noise variance. The second source of variance is initialization variance. You can see that these two kinds of variance peak at the interpolation threshold, so p when p is equal to n, and then they both reduce when we overparameterize. Okay, so this is already giving us the intuition we already had on the fact that as we overparameterize, we're killing some variance. And then what happens for the two last terms? Well, the sampling variance increases like the other source of variance, but then reaches a plateau threshold, and the bias is huge and then also reaches a plateau. And so this is why we called our paper the double troubles, that we have these two kinds of variances which explode at the interpolation threshold and the other ones which reach a constant value. Now, we can also study explicitly in this model what happens if we average the predictions of differently initialized random feature models. So let's say we have K models. They all learn from the same data set, but they have different first layers. And then we average their predictions. So what do we get in terms of test error? So when K is equal to 1, we get this double descent curve. And we see that as we increase K, basically everything, all this region around the interpolation threshold, the test error is reduced. Okay, and in particular, we can calculate analytically what we get when K goes to infinity. And what's really interesting here is that when you have an infinite number of networks you ensemble on, you see that the error basically becomes constant and then stays flat after the interpolation threshold. And this is, if you remember, exactly what we observed for neural networks. If we ensemble a lot of neural networks, then the test error basically becomes constant after the interpolation threshold. What's also very interesting here, so as I was saying, yeah, these two sources of variance are also killed as we overparameterize. What's very interesting here is that the final error you get when you take a single model but make it infinitely wide, so if you take this blue curve and you go to infinity, is exactly the same error as if you take an infinite number of overparameterized model. So you see that this plateau value in red is exactly the same as the final, the limit error of the blue curve. And so this is telling us that you can take one single model, make it infinitely big, or take one big model and then duplicate it a large number of times. Essentially what you'll get is equivalence, and it's given by the kernel limit error, which is the error you get for infinitely wide random features. So let's finish by just summarizing what we just saw. So what we did is we decomposed the double descent curve into bias and variance. And what we saw is that in the underparameterized regime, we indeed see this U-shaped curve up to the interpolation threshold, where the bias goes down and the variance goes up, just like we believed in classical learning theory. But what is different is what happens when we go beyond this classical regime. So in the overparameterized regime, well, what happens then is that the bias stays constant, but the variance is reduced. And this is really key to why neural networks are powerful when they're overparameterized. Are there any questions on this first part? Great. Okay, so let's move to our second part. just to check, can you still hear me? Because I'm always a bit worried that that
Yeah.
I lose. Yeah, great, perfect.
Great.
Great. Okay, so second part of this talk is going to try and distinguish this modern double descent, so the one of neural networks, with the one which was observed. I actually cheated a bit when I introduced double descent through the linear model, because as you're going to see here, the two types of overfitting are not exactly the same. So let's go back to our modern double descent. So as we said, so we have a training set with n examples. And what happens is that if we have more than, so if we have p parameters and we have a larger, n is larger than p, at some point we can't overfit the training set anymore and our training loss goes up. This is what we called the interpolation threshold. And we saw that we get a peak in the test loss at the interpolation threshold, okay? And okay, so this is what we call in the language of this paper, the nonlinear peak. Now, what would happen if we traded our nonlinear activation function, such as ReLU, for a linear activation function? Well, essentially, we'd just have a linear network. And it's quite easy to show that for a linear network, you only have, even if you have a lot of parameters, a lot of them are redundant. And the number of effective parameters you have is only equal to the input dimension D, which means that the interpolation threshold is much earlier, right? Because you have a much less fitting power. And so what's going to happen is that your interpolation threshold is going to occur when n is equal to D, okay? And correspondingly, the overfitting peak for the test loss is going to occur when n is equal to D. And so we're going to call this the linear peak. So if we represent this linear peak in a Pn phase space, as you can see on the right, it's just going to be a vertical line, whereas the nonlinear peak was a diagonal line. Okay, now one interesting question is, what would happen if we had a weakly nonlinear activation function? For example, like a tan H with a really high saturation value, right? It would be mostly linear around 0, but then it would have some saturation value, which would make it nonlinear. So maybe you could say, okay, maybe the peak will be somewhere in between n equals D and n equals to P, or maybe you'll have only one of the two. Well, actually, what we showed in this paper is that you can actually see both peaks simultaneously. And yeah, here we're going to really try and understand. So this is telling us that these two peaks are not the same thing, right? Because you can observe both of them simultaneously in one single neural network. And so we're going to try and see what distinguishes these two kinds of overfitting, right? The one that was for linear models, which was studied in the 90s, and the one for nonlinear models, which was studied in the early years, in the recent years. So we're going to use exactly the same model as before. So Gaussian inputs and ground truth with some added noise. The task is going to be the same. So it's going to be just mean square regression with added regularization. And so here I just wanted to reintroduce the notations of our random feature model to highlight one quantity which is going to be important, which is Z. So as I mentioned briefly before, Z is what we're going to call the projection of X, the inputs, through this layer of weights and then through the nonlinearity. So it's kind of a projected inputs data set. Okay, and when we're doing random feature regression, all we're doing is learning basically this linear function, which is the second layer, on the projected data set. Okay, so it's a linear regression on Z. And as we saw in the Marchikov-Pasteur example at the beginning of the talk, what's really important when you do linear regression is the covariance matrix of your inputs. In this case, it's not going to be X transpose, it's going to be Z transpose. And so to try and understand when we get overfitting, what we need to do is study this matrix, this covariance matrix Z transpose, and try and see when it has very small eigenvalues. And then we're going to confront the results of this random feature model with what we'd obtain with a teacher-student task, where basically we have our learning model is a 3-layer network, and it learns from the labels of a 3-layer network also. And here we can also mimic regularization by adding some weight decay. Okay, and so here I'm skipping right to what the results you obtain. So here I'm showing two plots, which are the test error. And I plotted them in this 2-dimensional axis where we vary the number of training examples on the bottom, on the axis, on the abscissor, and then on the number of parameters on the y-axis. Okay, let's start with this left plot, which is what we obtain for the random feature model. What you can see that is that indeed we get these two lines which I defined previously, which are the line n equals to p and n equals to d, where you do get overfitting. As you can see, the test error becomes red. So basically you get these overfitting peaks, which is indeed showing that we have this, and this is why we call this curve the triple descent, is that if you're walking along a line of constant p over d, so you're just increasing the number of parameters the number of training examples, then you're going to come across two peaks, the first one as at n equal d, and the second one at n equal p. On the right, actually exactly the same, which is surprising actually, because p in this case doesn't have the same meaning. In the random feature model, p was the number of blue nodes, so just the size of the hidden layer, whereas on the right side, p is the number of total number of parameters, so it's all the weights combined. But still, you get the peaks exactly at the same regions of this phase space. So here I'm going to go into a bit more of a technical part, so feel free to let me know if I should skip a bit, but I'll try and be really short on it to try and explain where these two peaks come from. So as I said, what we need to do to know where the peaks come from is to study the eigenvalues of the covariance matrix. And it turns out that in the high dimensional limit, the nonlinear activation function essentially becomes equivalent to, it becomes described only by two parameters, which are denoted here as eta and zeta, the ratio of which defines a degree of linearity of our problem. So here we can vary it between 0 and 1, for example, by going from absolute value in blue to this linear function in yellow. And if we plot the corresponding double descent curves, well, one would believe double descent, but actually here we see it's a triple descent curve, is that we see that as we make the model nonlinear, so going to the yellow, we see that the linear peak at n equal d becomes higher, whereas the nonlinear peak becomes smaller. So you can really see that the degree of linearity is regulating the importance of these two overfitting peaks. So to try and show you where this comes from, so what we did is we decomposed in the high dimensional limit. We can see that the action of the nonlinearity is essentially equivalent to a linear part plus a nonlinear part. And these two parts give different contributions to the spectrum of the matrix, so its eigenvalues. If we only look at the linear part, what we see is that we get vanishingly small eigenvalues in the spectrum when n is equal to d, as one can expect. This is what we observe in linear models, right? If we only look at the nonlinear parts, we see that we get very small eigenvalues instead when n is equal to p. Now, what happens if we combine these two parts together? How do they interact with each other? Well, if we take something intermediate for the degree of nonlinearity, what you see is that we still get these vanishing eigenvalues we saw for the nonlinear case. However, the n equals d curve is somehow cut off. So we don't anymore get the vanishingly small eigenvalues of the linear part, because essentially they're regularized by the nonlinear part. This is what we're going to call implicit regularization. So the nonlinear peak is still there, but the linear peak is implicitly regularized as soon as you add nonlinearity. Okay, so second thing that I wanted to show is to try and understand where these two peaks come from is to decompose, again, as we did previously, into bias and variance. And what we see on this left-hand plot here, when we have noise in the labels, is that the error is dominated by the noise here, and the noise peaks both for n equal p and n equals to d. So you can really see that it reinforces the two peaks. And this is very different from the initialization variance, which only peaks when n is equal to p. And this kind of makes sense, right? Because if we think of the n equals d peak, which is the one of linear models, well, it makes sense that initialization doesn't contribute to this because linear models don't have any notion of initialization, as I was saying previously. And what's interesting with this, so yeah, I'll just repeat again, the linear peak is caused by the noise, whereas the nonlinear peak is caused both by the noise and initialization variance, as we called it double trouble. And This explains an interesting thing, which is that in neural networks, you can get an overfitting peak even if you have no noise in the labels. And the reason for that is that your nonlinear activation functions essentially create an internal form of noise, which is overfit, even if there's no noise in your data. That's something which is very surprising and that we can really understand through this phenomenon, this theory. Now, second important difference between the linear and nonlinear peak is how they interact with regularization. So as I showed in one of the first slides of this talk, where I showed that in neural networks, if you regularize, then the overfitting peak is killed. Well, this indeed we observe along the line n is equal to p here. As we add weight decay, it's basically killed off. But you can see that the n equals d peak, so the linear peak, survives here. And this can also be seen so if you also remember, when we did early stopping, we killed the nonlinear peak. But you can also see here in these time plots that if you do early stopping, again, you kill the nonlinear peak, but you can see that the linear peak survives. So basically, to summarize, the linear peak survives regularization and early stopping. And the reason for that is, if you remember our theory part on the eigenvalues, is that it's already implicitly regularized by the presence of the nonlinearity. So it better survives regularization, whereas the nonlinear peak, which is due to basically overfitting internal noise in the model, is easily suppressed if you regularize. Okay, so that's it for the triple descent paper. If there are any questions, otherwise I can just move on to the next part, and then we do all the questions at the end.
So if we can just conclude from this results that it's essential to at least have an order D number of samples to at least get rid of even in the linear case, we need if we want to get good test error, at least order D samples are sufficient needed.
Yeah, pretty much. Exactly. And of course, that's typically the case in neural networks. I mean, we have, of course, generally we have, we have much more examples than input dimensions. Yeah.
I mean, that's not very obvious, because if you consider the images, then their dimensionality is quite high. So that actually justifies that you need lots of images, and less samples, high dimension images don't actually train any neural network properly.
Yeah, you're right. Yeah, D is equal to it's true, like 50,000 something like that in images. So you're right. I mean, to be fair, like we do see that this overfitting peak when n is equal to D is only along the n equals D line. Like before, you can see the test error isn't that bad when n is smaller than D here. So I mean, it's not that obvious. I mean, typically, yeah, you will want n larger than D to actually reach good performance. But if n is smaller than D, you don't have this overfitting problem.
Okay, thanks.
So I'm just going to conclude by extending this random feature model to a more realistic model, because you can definitely criticize these results for studying a really simplistic setting for the data. Right? What is key to learning and deep learning is the fact that the data is generally it has some structure, right? It has some low dimensional structure which you're trying to extract. It has an intrinsic dimension which is much smaller than the actual dimension of the data. That is completely ignored until now, because we just take structureless data, which is sampled from a Gaussian. And also we only considered mean square error, so regression problems. And what we'd really be interested in seeing how this interacts with classification problems, and in particular, how the loss function you use interacts with the double descent. So this is what I'm going to discuss in this last part. So what we're going to consider now is, so we're going to keep our random feature model, but this time we're going to do a classification task, which means that we still have a linear model generating the labels, except that this time it's going to be sent through a sine function, which is going to give us plus or minus 1 labels. And instead of corrupting with additive noise, we're going to corrupt it with label flipping, which is basically a Bernoulli variable, which can flip the labels with a certain probability. And so our objective function that we're trying to minimize isn't anymore going to be given by the mean square difference, but by a loss function L, which can be, of course, the mean square difference, but it can also be a logistic loss. And that's typically what we're going to be interested in. And the second thing I wanted to complexify a bit is our data model. So as I was saying, classic data sets we use in practice have a low dimensional structure. They have an intrinsic dimension, which is much smaller than the ambient dimension of the data. And so to mimic this, what we're going to do is we're going to separate our input space into two blocks. And one of the blocks is going to be much smaller than the other one. Say, for example, the small block is only 10% of the dimension of the ambient space. And these two blocks are going to have different variance. So we can adjust the variance of each subspace. So if we compare, for example, here to the isotropic setup where our data was a Gaussian blob, here, I hope you see my mouse, by the way, otherwise this must be very confusing. Yeah, here basically we have a salient subspace which has high variance and which is very small, and then we have a weak subspace which has small variance but is much larger. And what's also interesting is to study how much of the task is contained in the salient subspace, right? Because our teacher function, it lives in the input space, and we can choose to put it either in the strong subspace, in which case the task is going to be easier because the data is going to give you more information on the teacher, or we can put it in the weak subspace, in which case the task is going to be harder, right? Because you get less information on the teacher at each data sample. And we're going to call these two setups the aligned setup and the misaligned setup. So just to summarize, we have three setups. We have our isotropic setup of before, where the input space has the same variance along all dimensions. And then we have this strong and weak features model, where we can either put the ground truth in the strong space or the weak space, which is aligned and misaligned. And what we did here is that we had to completely change our calculation method, because actually it turns out the classification problems are much harder to study. You can't simply use random matrix theory methods to study these kind of problems due to the nonlinear loss function. And so what we had to do is use some statistical physics methods based on the replica trick, which basically give us the generalization error as essentially an angle between the teacher function you learn and the student function you learn and the teacher. So basically, the more aligned you are with the teacher, the lower your generalization is going to be. And yeah, one thing we definitely observe, so let's start by looking at what happens for square loss. So for square loss, if we look at the blue curve, it's essentially what we had in the previous part of the talk. So we have the double descent curve, except that in this case, we're looking at a classification problem. So you can see that the test loss starts from random guessing at 0.5, it's binary classification, and then it goes down, has a peak, and then is reduced. Now, if we make the data set harder by considering the misaligned scenario, you see that you get more overfitting around the interpolation threshold. So the orange curve is a bit higher than the blue curve. But if you make the data set easier by putting the teacher in the low dimensional subspace, which has strong variance, then you can see that the task suddenly becomes much easier. In some sense, the random feature model is beating the curse of dimensionality in this case, and it kind of manages to ignore all the useless part of the inputs to really focus on the salient features, which are those that the teacher uses. Now let's look at what happens if we trade our square loss for a logistic loss, or a proper classification loss. So what we can see is that in the case of isotropic inputs, the final error we get for the very overparametrized model is pretty similar, actually. However, one thing we see is that the overfitting peak is killed. And we're going to see later how this happens, how we get this implicit regularization. And again, if you make the task harder, well, you see that the test error is going to go up. Here you actually see a larger gap than before, but the gap is even wider if you consider the aligned scenario. So you can see that for the easy dataset case, the test error really goes to a much lower value than for square loss. And this is telling us that logistic loss performs particularly well for low dimensional tasks. And as I said previously, it induces implicit regularization. So really, the loss function has a strong impact, the data structure have a strong impact, and their interaction is non-trivial. Let's see this a bit closer by now studying the training loss instead of the test loss. So this is something we can actually calculate in in the random matrix setup we studied previously. Here, thanks to the statistical method, we can calculate the training loss. And what's very interesting here is that you see that for square loss, the point where the training loss gets to 0, so the interpolation threshold, doesn't depend on the type of data we feed in. This is something which is kind of surprising, right? I mean, you're given much easier data, but the model, and so the test loss is much lower, but the model still needs as many parameters to perfectly overfit the data. And this turns out not to be the case if you consider logistic loss. So for logistic loss, you can't really define an interpolation threshold because the training loss is never strictly 0. But if you look at the point at which it kind of reaches the plateau, it's much earlier for the aligned scenario, which means that you manage to overfit much quicker for the aligned scenario with the logistic loss. And so, yeah, really you can see here that logistic loss helps you fit easy data sets more easily, whereas the square loss has as much difficulty for the 3 types of data. Third thing I wanted to show you is some behavioral differences between these 2 losses to try and explain why we had this implicit regularization. So here what I'm plotting is the norm of the estimator we're learning. So essentially the norm of the second layer weights of the random feature model. And so if we start looking at what happens for square loss, so as we could expect, we get this peak at the interpolation threshold, and then we reach a constant value. Okay, and it makes sense that we reach a constant value because we're looking at really the square difference between the outputs of the student and the teacher. And so the student has to have the right norm, which is bounded to get the right labels. That is very different if you look at logistic loss, because what you do for classification losses like the logistic loss is that you take the output of your student and then you feed it through a sigmoid function, which squashes it between 0 and 1, or -1 and 1, depending on if you took the label 0 and 1 or -1 and 1. And what's interesting here is that the norm of the student keeps increasing as we overparameterize. In some sense, the model is becoming more and more confident. And what's interesting is that when the data is easier, so in the aligned scenario, you can see that it increases even faster. The overconfidence is even more strong. So really, the logistic loss gives an advantage for easy data sets because it can really detect the easiness of the data set and become more confident. And in particular, this increase of the norm of the estimator kind of shields away the overfitting peak, because we saw in the square loss, this overfitting peak was due to a large norm of the estimator. Here, it doesn't matter to have a large norm because in any case, your outputs are squashed between 0 and 1. And so this is really what induces some implicit regularization for classification, is the fact that you only look at the sign of your labels or the probabilities if you apply a softmax. And yeah, so that's it for me. So thank you very much for your attention, and open to any questions.
Thank you, Stéphane. We have a question from Eric. You wrote it in the chat, but perhaps you can.
Yeah, I can ask it directly. So first of all, great presentation. I really enjoyed it. So this thing you showed us with this logistic loss and how it interacts with with this peak. Does it extend to categorical cross entropy?
Yeah, that's a very, so by categorical you mean like multi-class, right?
Yes, yes.
Exactly. Yeah, that's a really good question. So the problem is in our setup, it's actually very non-trivial to extend the binary setup to multi-class. So we haven't been able to study that question at all. I would kind of expect yes, and actually we do observe that in like classification tasks. I mean, I've been talking about double descent for like 45 minutes as if it's a huge thing, but really in neural networks, like practitioners aren't really afraid of of double descent, right? And one of the reasons for that is that you get implicit regularization from your sort of SGD-based learning, but also I think because we mostly study classification tasks, and in classification you less get this sensitivity to the norm of your estimator, because in any case you're just looking at probabilities, and it's fine to be overconfident. So I expect to some extent, yes.
So when I'm on the floor, I just we discussed the images and input dimensional additive images before. I think an important thing to mention there is we typically use a very special kind of architecture to essentially make the dimensionality of the input much smaller. So each image kind of contributes, the number of image patches on the first conv layer to your model. So I think it's an interesting question of how to actually analyze that.
Yeah, actually, to go further a bit on that question, I was kind of thinking about it after you asked. We did try and plot these triple descent curves. So let me show them again. These phase spaces. Yeah. So this phase space here, you could see for the neural network. Actually, the neural network was trained on a very unconventional task for neural networks. It was trained on a teacher-student task. So it's learning from the labels of a neural network, which is a very difficult task because these labels are very chaotic. And so the intrinsic dimension of the task is basically equals to the actual dimension. We tried the same thing on real data sets like MNIST and CIFAR-10, and you can see the curves in the paper. What you observe in that case is that this linear peak at n equals to d is much wider, and it goes down very, it basically extends down from n equals to d to n equals 0.2 d or something. And basically, the explanation for this is that really the linear peak occurs not at n equals to the dimension, but n equals to the intrinsic dimension. But there isn't a single intrinsic dimension. In fact, if you look at a data set which has several, if you consider, for example, a strong and weak features model where the input space is separated into two blocks with different covariances, well, actually, instead of seeing one linear peak, you're going to see two linear peaks, one for each size of the data set. One for each size of the blocks. For example, if you have a block of size d over 3 and the rest, which is of size 2d over 3, you're going to have two peaks, one at d over 3. And so for CIFAR-10, you can kind of view CIFAR-10 as like hierarchical loads of blocks together, which is basically a mess. But basically, instead of having a well-defined peak at n equals to d, you're going to have this whole overfitting region when n is smaller than d, which is very wide. And you'll see the curves in the paper. And so, yeah, that was actually a better response to your question earlier.
Do we have some more questions? Erik has one.
Yeah, but I'll leave the floor to someone else before I ask mine. Well, no one jumps in. So, yeah, you mentioned in your bio that you are interested in understanding the inductive biases of transformers. Could you just give us a teaser on that?
Sure. So one line of research we've been working on is trying to determine how much inductive bias you need for a particular task. And we started this research direction by taking, basically, our idea was, how come CNNs find better solutions, better generalizing solutions than fully connected networks, in spite of the fact that a fully connected network could, in principle, represent the function of a CNN? Why does it not find this solution? What we did to study this question was to train a CNN up to a certain point and then embed it into fully connected space. In other words, rewrite it as a fully connected network which is very sparse, and then continue training. And basically what we saw is that if you do this, it actually works, and you can get your fully connected network to perform better than the CNN if you train the CNN for long enough, if you constrain the fully connected network basically to this kind of CNN subspace. And this was kind of intriguing, but of course not at all useful, because like fully connected networks have way more parameters and are very costly to train. So what we did is instead we considered the idea of biasing a transformer, which you can also see just like a fully connected network is a more general architecture than the CNN in the sense that it can represent a CNN, bias the transformer towards a CNN early on during training. And this is what we did in a model called convit. So basically the idea is you take a transformer, but you just initialize it in such a way that it behaves like a CNN at initialization, just like the fact that you can initialize your fully connected network as a convolutional model. And what we observe is that this kind of helps the transformer in terms of sample efficiency, right? Because one of the problems of transformers is that it has a very general, it has a very free inductive bias compared to the CNN, which have very strong inductive bias. And so giving it more inductive bias helps it on easier tasks, but still gives it the freedom to, like, if it has enough data, to learn more complex functions than CNNs. So yeah, that's what we were studying.
That's interesting. Have you seen similar similar or done similar experiments with graph neural networks, since I mean it's a very similar extension. So just like you can, I guess you induce the convnet structure by initializing the key and query matrices in a particular fashion. You could you could design the attention function of the transformer so it initializes as the the adjacency matrix of the graphs you're interested in. I guess that doesn't have, no, that's just a pure, random ID.
I mean, I've never actually worked on graph neural networks, so there's probably, that's probably a very good idea.
You work with transformers, so you have, no, sorry.
Yeah, in some sense.
A transformer is kind of a generalization.
Yeah. I think, I mean, it's definitely an idea that is underexplored, is sort of starting from very constrained architectures and giving them more freedom as they train, sort of recovering degrees of freedom so that they basically adapt to the difficulty of the task. Like currently what we do is we take very complex models for very complex tasks and very simple models for simple tasks. And it would be nice if we could find a way to automatically adjust the complexity of the model to the task by learning the inductive biases, basically.
Yeah, and also freeing ourselves from this very, the infinite prior of a convnet, essentially.
Yeah. Since then, there's been about like 40 different papers introducing convolutions into vision transformers. So I guess it wasn't the most idea in the world.
What was the name of the paper, of the architecture?
For the convits, introducing improving vision transformers with convolutional inductive biases.
Great. So thank you very much once again. I have to run.
Yeah, thanks a lot.
Bye-bye.
Do we have one last question?
So do you have any final recommendation to how to train a neural network based on the three? I mean, because you don't have test error, you just have it on validation. So how long do you wait on the training curve to actually say that I have good enough model?
I think if I was to extract one recommendation, I don't believe at all that a practitioner, as I was saying, has to be wary of the overfitting, because this is really, I mean, as soon as you have the slightest form of regularization, even thanks to the optimizer you use, you don't really see these overfitting peaks in general. However, one thing that is very important, I'd say, is what you see in the first part of this slide of this talk, where I discussed the fact that once you do ensembling, well, basically, wait, let me find the correct slide. It's this one here. Let's get rid of this. Yeah, so what's really important is this curve here, where you see that you have the blue curve, which is for a single model, and the orange curve, which is for 20 models ensembled together. And the key insight here is that the optimal performance you can get is basically ensembling a large number of models just after the interpolation threshold. That's where you can get the best efficiency in terms of scale of your model, basically the best computational cost to error ratio. And this is nice because we can really understand this from our study of the random feature model, the fact that basically what's happening is that once you're past the interpolation threshold, all you're doing is reducing variance by overparametrization. And this is actually a rather slow way to reduce the variance. A much more efficient way is to split your capacity into separate models and then average their predictions together. I think that's really the key takeaway for training models in practice.
So interpolation threshold is P equal to N, right?
It's P of order of N. In neural networks, a bit more complicated because, well, it's not exact. And it depends on your activation function. It depends on, but basically it's always at P equals to a constant times N, where the constant isn't too far away from 1. But you can see it very easily by just seeing when your training error goes to 0. However, this recommendation only really, I mean, I'd say it wouldn't apply to like state-of-the-art training, because in state-of-the-art training, what you do is you have a lot of augmentation, and therefore basically you never get down to 0 training error. In practical applications, you never really overfit your data set. You always apply a lot of augmentation. So this is really a recommendation for if you train on a finite data set and you don't do augmentation.
Great, thanks.
But I mean, even with augmentation, I suspect that ensembling is one thing which is I'd say understudied simply because it's nothing new, and so people don't really publish papers in ensembling, because I mean, it wouldn't be a very interesting paper if you just took two state-of-the-art architectures and ensembled them together, right? It wouldn't have much added value. But for practitioners, I think since there are less papers on ensembling, they kind of forget the power sometimes of ensembling. I mean, something which is, of course, very common in classical machine learning, like, random forests and stuff like that. But even in the context of neural networks, just training two networks and averaging them may be better than training a twice larger architecture in some cases.
Thank you, Stéphane, for coming here. And we'll take a break for the holidays, and then we're back January 13th with Andrew Jessen from Oxford Applied and Theoretical Machine Learning Group. He's going to talk about head in the clouds, why decision-making is hard. Thank you for today.
Yeah. Bye.
Bye-bye.
Thank you.
Thank you.
Thank you. Bye.
Bye.
Thank you. Bye.